In this segment, what I want to talk about is partial application of functions and this idea of curried functions, which exposes the mechanism by which partial application works. Suppose we've defined that the function multiply xy equals x times y. And it looks like multiply xy takes two arguments, and if we give it the arguments 2 and 3, indeed we get out the result 6. But what happens if we just apply it to one argument, 2? What you can see we're left with is something that's waiting for another argument and can then give a result. So it's the function that takes the argument y to the result 2 times y. So the partial application of multiply to 2 gives us back the function that multiplies its argument by 2. So if we make a partial application, then we get a function as a result. So suppose we want to double all the elements in a list. We can do that by applying map to the function multiply 2. That will give us a function that, when given a list, will map multiply 2 all the way down the list. So multiply 2 is the function that multiplies by 2. Map of multiply 2 is a function that multiplies every list element it gets by 2. And so these partial applications give us another way of returning a function as a result. We saw how to do it with a lambda earlier, but this does it without introducing a lambda, simply by not passing the function, as it were, enough arguments. So partially applying it to one instead of two arguments gives us a function, as is illustrated by this. This is the picture that motivates what's going on here. You can see it's waiting for an input, and when it's got that input, it can give the result. Now, what is it that's going on? Does multiply have one argument? Does it have two arguments? What's happening? Well, what Haskell contains are what are called curried functions. And in Haskell, every function takes exactly one argument. So the multiply function takes one argument, for example, multiply applied to 2. And what it returns in that case is a function. So when we apply it, the result to 3, we get an integer. So what we're doing here is we're applying multiply first to 2, and then we're applying the result, multiply 2, to 3. So every function takes exactly one argument. This is called curried function representation after Haskell curry, the Haskell in the name of the programming language we're learning. So the curried idea is that it's sort of a pun on the British number one food, curry. So the functions are curried to make them more spicy, if you like. They just take one argument, whatever. So that's what's underlying this. And just as an example, if we go back to our definition of comp2, which you see at the bottom of the slide, we say comp2 applied to f and g is the function that takes x and y to g fx fy. We get exactly the same effect by writing comp2 applied to 4 arguments, f, g, and x and y, giving the answer g applied to fx, fy. If we only apply it to 2 arguments, we get precisely that function. So again, we're able, in some situations, rather than using a lambda to give us an explicit function, to get a function as a result simply by partially applying a multiple argument function. Now, this has some impact on associativity. If we write an application multiply to 3, that means first apply multiply to 2 and then apply the result to 3. So that means application is what's called left associative. When you've got a choice, you always bracket to the left. Going alongside that, arrow is right associative. When we write int, arrow, int, arrow, int, we mean int, arrow, int, arrow, int. So that means when you multiply to one int, what you get back is a function from integers to integers. So it makes sense, only makes sense, the way you've been writing arrows, for arrow to be right associative. So application is left, you bracket to the left. Corresponding to that arrow, you bracket to the right. And that's important. Arrow is not associative. A function from int to int to int looks like this image we see at the top here. It takes 2 integers, returns an integer. If we bracket it the other way, g takes a function from integers to integers and returns an integer. So those are entirely different patterns of behavior. The first one, for example, takes 2 integers and perhaps multiplies them together. The second one takes a function from int to int and somehow extracts an integer, perhaps by applying the function to 0. But the message here is that arrow is definitely not associative. Now we can write functions that convert between curried and uncurried representations. You can see in here a diagram of what goes on inside uncurry of f. What uncurry of f does is to take a function f which is curried and get it to apply to a pair x comma y. And what we have to do there is we have to first split the x and y into 2 components and then only then apply f to them. And in a similar way, if we want to turn an uncurried function into a curried one, we have to take the 2 arguments separately and combine them into a pair before we apply the function. And I leave it as an exercise for you to define those functions uncurry and curry. And you can use partial application there to make the definitions more straightforward. You can use lambdas if you wish, but you can also use partial application. Now we've talked about partial application of functions, but Haskell also has a really neat idea of what's called an operator section, which is just another word for a partially applied operator. And operator sections are written in parentheses, and here are some examples. Parenthesis plus 1, close parenthesis, is the function that adds 1. So we've partially applied the operator to its second argument. Parentheses 10 plus partially applies it to its first argument. Greater than 2 tells you, is the argument bigger than 2? The operator section 3 colon is the function that puts the number 3 on the front of a list. The operator section $1 is the function that applies a function to the value 1. And plus plus, string with new line in it, adds a new line character to the end of a string. So we get those, and this is something we use all the time without really thinking about it. So if we want to double all the integers in a list, we can say map times 2, or indeed 2 times. And that gives us 2 times 2 is a function to double a single value, and we map that along a list. And if we have a list of functions that we want to apply in turn to a single value x, then we can map the function apply me to x along the list of functions. So we map the partially applied application operator, dollar applied to X, along the list of functions. And that means each function in the list gets applied to X. Now with operator sections, you can see that what we've done here is we can sometimes put the argument on the left, sometimes on the right. Whereas with functions, how can we partially apply a function to its second argument? Suppose we want to define a function that tells us whether or not a character is a member of the list of whitespace characters that we've defined. Is the character whitespace or not? We can't apply the function lm directly to whitespace. So what can we do? There are in fact three nice alternatives here. The first is to define the function explicitly that says lambda ch apply lm to ch and whitespace. So that's the function that takes a character to lm applied to that character and whitespace. Alternatively, we can flip the function lm so it takes the two arguments in the opposite order and then partially apply it to whitespace. Or as a third thing, we can turn it into an operator section by putting lm in back quotes and then applying it on the right hand side to whitespace. So we have a number of tools we can use. The most general is to use the lambda. The other two apply only to the second argument, whereas using an explicit lambda allows us to partially apply to the first, third, seventh and 91st arguments, for example. So in this segment, we've seen partially applying a function gives us a function back as a result, and indeed every function, which looks perhaps like a 2 or 3 argument function, in fact is a function that takes one argument and returns a function to be further applied to the second and third and fourth arguments. And that's what's called curried functions, and it gives us a way of returning functions as results without explicitly having to use a lambda.